Welcome to the SAR channel, where sound and audio are demystified. The Internet is a worldwide system of connected networks that allows different types of data to be sent to one or many users. A network is a group of computers that share resources, and the Internet links many such networks together. The main benefit of this connection is that the more systems are online, the more resources each user can access. Voice over Internet Protocol, VoIP, is a technology used to send speech and voice messages over IP networks like the Internet using packet-switched data. Simply put, VoIP is making a phone call through the Internet. It works by turning an analog audio signal into digital form, compressing it, breaking it into IP packets, and sending it across the Internet. The receiver's system then reverses the process. VoIP operates separately from the traditional public telephone network, PSTN. It is also known as Internet telephony, IP telephony, broadband telephony, or voice over broadband, VOBB. VoIP offers efficient bandwidth use and low call costs, and is used by both individuals and large organizations. In some systems, voice data is encrypted for security. In transport mode, only the audio data is encrypted, while in tunnel mode, the entire packet is enclosed in a new, secure packet. File formats like MP3, WMA, and AAC are popular for sharing and downloading music online. These compressed files make it easy to store and send music efficiently, but they also allow illegal sharing of copyrighted material. Digital rights management (DRM) systems are designed to protect this content. They encode music for online distribution, storage on portable players, or recording on disks, setting rules for how the files can be used. DRM systems control access to copyrighted content, limit copying, and detect illegal versions. Their goal is to ensure safe and fair exchange of digital property. Although there is no universal DRM standard, several systems exist to manage how protected music can move between formats and devices. An ideal DRM system should work on all platforms, use little processing power, be revocable and renewable, and remain reliable, flexible, and easy to use without being intrusive. DRM goes beyond simple copy protection. It defines how much copying is allowed and ensures creators get paid. However, DRM must also respect users' convenience and rights. Its challenge is to stay effective while remaining user-friendly. In practice, DRM discourages casual piracy, but cannot completely stop skilled hackers. Legal measures are therefore needed to deal with professional piracy. A major problem is that once a few hackers create tools to bypass DRM, those tools can spread easily, just like the music files themselves. In many cases, protecting copyrighted music from both serious and casual piracy is essential. Encryption is used to stop copying, watermarking helps identify who owns the content, and fingerprinting helps recognize the content itself. These protections must stay strong even when the content is shared or used on different devices and formats. An ideal protection system should include rights management, usage control, authentication, piracy prevention, and tracking features. Still, for these technologies to be truly effective, they must also be backed and enforced by legal regulations. Digital audio watermarking is a security method that hides ownership information directly within the audio data. It can verify authenticity and trace piracy by embedding an inaudible digital code or tag into the audio. Source watermarks link content to a specific medium, like a DVD or Blu-ray, while transactional watermarks track usage independently of the media. Watermarking, also called steganography, sometimes uses encryption to enhance security. Watermarks must be inaudible to listeners and not affect sound quality. They should be robust enough to survive processing, format changes, and compression while remaining secure against removal or tampering. If a watermark is attacked, it should degrade the audio or show evidence of interference. Watermarks must also avoid false positives, detecting watermarks where none exist, and false negatives, missing an actual watermark, and must not add excessive data overhead. Simple watermarks use just a few bits, making them easier to embed and more resilient, but they can be less secure. Security can be improved with techniques like cryptographic keys. Watermarks can be applied to different file formats, PCM, WAV, AIFF, in mono or multi-channel recordings, and at various sampling rates and word lengths. Many watermarking methods exist, including manipulating phase, embedding data in inaudible frequencies, or using spread spectrum encoding. Often, multiple methods are combined for greater reliability. Copy control watermarks prevent casual copying, allowing limited or no copies, while forensic watermarks deter professional piracy, embedding detailed data to verify authenticity and detect tampering. Some systems, like MP3 ID 3 tags or track unique identifiers TUID, automatically embed song and album information to track content sold to authorized users. Embedded watermarking is used in professional audio formats like DVD audio, Super Audio CD, SACD, and Blu-ray, and similar techniques can also protect CDs. Audio fingerprinting, or content-based audio identification, works by analyzing an audio file to create a unique fingerprint, and then comparing it to a database to identify the file. Fingerprints are mainly used for licensing and copyright enforcement, but they can also help recognize musical features and recommend similar songs to listeners. An audio fingerprint is like a summary of the file's key characteristics, allowing it to be efficiently searched and identified among many files. During a training phase, features from known audio are stored in a database. When an unknown file is analyzed, its fingerprint is compared to the database, sometimes containing millions of fingerprints, to find a match. The system then outputs metadata, identifying the file and a confidence level. Although fingerprinting shares some similarities with watermarking, it serves a different purpose. Unlike a file name, which can be easily changed, a fingerprint directly identifies the content itself. Ideally, the fingerprint remains valid regardless of audio format, sampling rate, equalization, or distortion, and can still be extracted after processing or alterations. It should also resist forgery or reuse on other content. Fingerprinting generally involves two steps: extraction, where the fingerprint is created, and modeling, where it is analyzed and stored. The final step is searching the database of known fingerprints to identify the unknown audio file. Streaming audio is when a file is compressed enough to be played as it is received without waiting for the full download. Playback starts once a buffer is filled with incoming data. Compression helps reduce file size so it can be delivered quickly, but streaming continuously in real time is more challenging. Audio streaming must handle the Internet's packet switching method, where packets can arrive out of order or be lost, requiring retransmission and causing delays. A buffer is needed to prevent interruptions in playback. Additionally, streaming must account for different computers, processing power, and internet speeds, as well as varying network conditions and traffic. These challenges increase when streaming video alongside audio, especially if both need to stay synchronized. The internet connections vary from mobile phones to high-speed corporate networks, leading to very different data rates. High-bandwidth streams work well for fast connections but can cause buffering for slower users. To address this, servers can reduce the stream's bitrate, stream thinning, to prevent interruptions, though this can lower quality, especially for audio. Another solution is to create multiple versions of the same audio at different bit rates, allowing the server to send the most suitable stream for each user. Dynamic bandwidth negotiation adjusts the stream as network conditions change. Encoders can create multiple embedded streams at different rates, and the server switches streams based on the user's current bandwidth or packet loss. The system must monitor bandwidth carefully. Too slow a response causes signal drops, while too fast a response can lead to unnecessary bitrate changes. The internet is good at sending data from one user to another, a process called unicasting, which works well for emails or direct music downloads. However, sending the same content to many users at once is inefficient this way. IP multicasting solves this problem. Using terrestrial broadcast, satellite, or cable, multicasting allows a single copy of data to reach many users simultaneously, similar to radio. In multicasting, special routers handle copying and delivering the data streams, reducing the load on the main server. These routers also provide timing information to keep audio and video packets synchronized. Even if only a few key routers have multicasting capability, the system can efficiently serve many users at the same time. If you've enjoyed this video so far, please hit the subscribe button for more. Thank you. The MPEG-4 standard, like MPEG-1 and MPEG-2, defines how to represent audio-visual content and is designed for multimedia communication and entertainment. It is backward compatible with earlier standards but goes further by supporting a wider range of applications and better interoperability with other technologies and formats. MPEG-4 is a set of coding tools for many applications, including interactive audiovisual content. Objects in MPEG-4 can include music, speech, movies, text, graphics, animated faces, web pages, or virtual worlds. A scene description defines the timing and spatial relationships between these objects. MPEG-4 focuses on very low bit rates and scalable bit streams, making it suitable for the internet, streaming, wireless, and digital broadcasting while supporting high-quality audio and video. It enables content-based interactivity by representing both natural and synthetic computer-generated audio and video as separate objects. These objects are transmitted or stored individually and then combined to form complete scenes. At the receiver, data streams are demultiplexed, objects are decompressed and composed according to the scene description and presented to the user. Because objects are individually represented, users can manipulate them separately. Scene descriptions also define the object's timing, spatial positioning, and behavior. MPEG-4 additionally supports intellectual property management and controlled access. Like other standards, it provides normative specifications for interoperability, along with non-normative guidance for implementation. MPEG-4 uses a system called Binary Format for Scenes (BIFS) to describe and change scenes dynamically. BIFS is based on Virtual Reality Modeling Language, VRML97, but instead of text, it uses binary code. Unlike VRML, BIFS supports real-time streaming of scenes and allows a high level of interaction between objects and the user. Objects can be positioned anywhere in a coordinate system, transformed to change their shape or sound, grouped into larger objects, or modified with streamed data. Users can also choose their own viewing and listening points in the scene. Users can interact with the content using local processing or by sending input back to the sender. While MPEG-1 and MPEG-2 focus on compressing, transmitting, and storing audio and video with minimal interactivity, MPEG-4 allows control over individual objects and their relationships and supports many different types of data. MPEG-4 applications include internet multimedia streaming, like a browser plugin, interactive video games, video conferencing, video phones, interactive storage media, multimedia email, networked databases, HDTV co-broadcast, remote emergency systems, video surveillance, wireless multimedia, and broadcasting. Users view scenes as the author designed them, but the author can allow interaction with the scene. MPEG-4 audio combines high-quality music, speech, synthesized speech, and computer-generated sounds into one system. It works for everything from simple mobile applications to advanced sound systems, building on existing MPEG audio codecs. It supports mono, stereo, and multi-channel audio. MPEG-4 handles wideband and narrowband speech, intelligible speech, synthetic speech, and synthetic audio. It also provides scalable audio coding, allowing the bit stream to adapt dynamically to different network or device conditions. With scalability, part of the bit stream can be decoded at lower quality and lower bit rates, while full streams deliver higher quality. This lets audio adapt to changing network speeds or decoders with different capabilities. Users can also select certain audio channels or frequency ranges for playback. Scalability is achieved through hierarchical embedding, where multiple bitstream subsets can be decoded independently or combined. MPEG-4 defines structured audio formats and a sound language for coding signals at very low bit rates. Audio is treated as objects, which can be single or multiple signals, mono or multi-channel, and can be grouped or mixed. MPEG-4 also supports audio composition, allowing control over synchronization, routing, mixing, tone, sample rate, reverb, spatialization, filtering, compression, dynamic range, and other effects. The standard defines a signal processing language for synthesis but does not fix a specific synthesis method, ensuring all MPEG-4 compliant synthesized music sounds consistent on any decoder. It also includes text-to-speech (TTS) capabilities, converting text into phonetic symbols and synthesizing speech with natural prosody. TTS can synchronize speech to video, adjust speed, tone, volume, and modify speaker characteristics such as sex or age. Scalable bit streams allow playback at different bandwidths depending on internet speed. A bit stream can include multiple layers. The base layer encodes at the lowest bit rate, while additional layers encode the difference between the original and base signal for higher quality playback. MPEG-4 version 1 was adopted in 1998. Version 2, finalized in 1999, added new tools but kept version 1 unchanged, making it backward compatible. Versions 1 and 2 were combined into a second edition of MPEG-4. Version 2 expands the standard's audiovisual capabilities and improves error robustness in audio algorithms. It also supports low-delay coding for music and speech. Version 2 introduces the harmonic and individual lines plus noise (HILN) coding tool and allows alternative coding methods in AAC, such as bit-sliced arithmetic coding (BSAC) or bitplane coding, and transform domain weighted interleaved vector quantization. The MPEG-4 standard includes earlier MPEG audio standards. In particular, it uses MPEG-2 AAC for high-quality audio coding. MPEG-4 adds specialized tools to AAC for more efficient compression. One tool is long-term prediction (LTP), a simple prediction method similar to those in speech codecs. LTP works especially well for stationary harmonic signals and reasonably well for non-harmonic tonal signals. MPEG-4 also offers Twin VQ as an alternative coding method for AAC. Additionally, MPEG-4 includes the audio lossless coding tool, which compresses audio while allowing bit-perfect reconstruction, supporting up to 24-bit resolution and sampling rates up to 192 kHz. The MPEG-7 standard, called the Multimedia Content Description Interface, is different from other MPEG standards that focus on compression and transmission. Instead, MPEG-7 provides ways to describe and analyze multimedia content in a standardized way, making it easier to identify, compare, and search large amounts of data. Most search engines rely on text-based metadata like keywords, titles, authors, or dates to find content. This information is often added manually and may not fully capture the content itself. MPEG-7 goes further by describing intrinsic characteristics of the media, allowing content-based searches. For audio, MPEG-7 can analyze waveforms and extract information automatically or manually. These content-based descriptors, also called feature vectors or fingerprints, help classify and describe the audio. A single audio file may have multiple descriptors, such as key signature, melody, instrumentation, and other content-based properties. Audio descriptors include low-level features like waveform and power, spectral descriptors, spectrum envelope, spread, flatness, centroid, signal parameters, fundamental frequency, harmonicity, temporal timbral features, attack time, temporal centroid, spectral timbral features, harmonic centroid, deviation, spread, variation, spectral basis representations, and silence descriptors. Other descriptors cover lyrics, key, meter, and starting note. Musical instruments can be classified as harmonic sustained, percussive non-sustained, non-harmonic sustained, or non-coherent sustained. Sound effects in speech can also be described. MPEG-7 also includes metadata for artist, title, copyright, usage rules, user preferences, browsing info, storage format, and encoding. It provides a description definition language based on XML schema, which defines how to use these description tools. Thank you for watching till the end. To better understand each video, make sure to watch the previous ones. Some may serve as prerequisites for the next. If you have any questions or opinions, feel free to leave a comment. Until next time, subscribe and stay curious.